Hi boys and girls, this is lecture 4.3 in Unit 4. The topic, Limits at Infinity. This concept deals with the end behavior of functions, what the function is doing as x gets very large or very small. So as x is approaching positive infinity, what's happening with the function value? As x is approaching negative infinity, what's happening with the function value? Often a function will approach a specific value as x increases or decreases without bound. This function value is often called a horizontal asymptote. So probably you have seen horizontal asymptotes prior to this course, but we're also going to recognize that as a limit of a function. As x gets very large here, you can see the function value is approaching 3. It's never going to actually get to 3, just get closer and closer and closer. We call that a horizontal asymptote, but it's also the limit of the function as x approaches positive infinity. That makes sense. The limit meaning it's a boundary. It's not going any further than 3. Similarly, in this function, as x approaches negative infinity, as x gets very, very small, once again, the function is approaching the horizontal asymptote 3. It's never going to actually reach 3. It's the limit or boundary of the function as x approaches negative infinity. It almost seems as though we could discuss limits at infinity and horizontal asymptotes as if they are the same thing. And notice here we're going to define horizontal asymptotes as a limit. The line y equals L, a horizontal line, is a horizontal asymptote of the graph of f if the limit of our function as x approaches negative infinity is L, that line, or if the limit of our function as x approaches positive infinity is that line. Now that we've established the connection between limits at infinity and the horizontal asymptotes, let's start looking at what limits at infinity would look like for certain types of functions. We'll start with rational functions. And notice here we have a simple rational function where the numerator is a constant and the denominator is a variable raised to a power. If r is a positive rational number, the exponent is a positive rational number, and c is any real number, some constant, then the limit as x approaches negative infinity of this rational function, constant over variable raised to a power, is 0. Or the limit of this function, constant over variable raised to an exponent, as x approaches positive infinity is 0. This is going to be very handy for us. Every time we see a function where there's a constant in the numerator and a variable raised to a power in the denominator, the limit of that function as x approaches positive or negative infinity is 0. But why is this true? Let's think about this rational function. If the numerator is a constant, pick any constant, let's say I have a 3, and the denominator is the variable raised to any exponent, let's just say x squared. What happens as x gets very, very large? 3 remains constant, but x continues to be a larger and larger number, making the fraction very, very small. And so you can see that as x is approaching infinity, this is going to be 3 over a huge number, which makes it a very, very tiny number. It's approaching 0 the larger x becomes, whether it's positive or negative, because you're raising it to a power and it gets to be a very, very large number. So understanding the characteristic of this rational function helps us to see why as x gets very large, approaching positive infinity, or very small, approaching negative infinity, this fraction gets very, very close to 0, approaches 0. And so that's why the limit as x gets very large or small with a rational function where the numerator is a constant and the denominator is a variable raised to any power becomes 0. Let's find the limit of this function as x approaches positive infinity, the limit of 5 minus 2 over x squared. Now if I rewrite this as the limit as x approaches positive infinity of 5, basically if we just think of 5 by itself, it's a horizontal line that obviously as you're approaching positive infinity is still going to be 5, it's not going to vary, but then minus the limit as x approaches infinity of 2 over x squared. Now we should recognize this as one of the rational functions we were discussing previously. As we sort of plug infinity into this denominator, and this denominator gets very, very large, then we know that the fraction itself gets very, very small. And the limit or boundary of what this value can become is 0. So essentially the limit as x approaches infinity of 5 is 5. It's going to be 5 from negative infinity to positive infinity. However, the limit as x approaches infinity of 2 over x squared is 0. So this limit altogether is 5. And you can see I have a graph of this function, and it's graphically depicting, of course, you can see here this is 5, this horizontal asymptote. As x approaches negative and positive infinity, the function is approaching the limit 5. Now we're going to find the limit of a different type of rational function. Notice the numerator is not a constant. It contains a variable as well. And if we attempt to evaluate this limit by plugging infinity in for both variables, we end up with infinity over infinity, which is known as an indeterminate form. And it doesn't really give us any information about the end behavior of this function as x approaches positive infinity. So we're going to use an algebraic technique to rewrite this function into a form where we are able to evaluate the limit. We find the highest degree variable in the denominator of the function. In this case, that's x to the 1. We then divide each term in the function by that variable. Let's do that now. We have 2x minus 1 over x plus 1, our original function. The highest degree variable in the denominator, x to the 1, therefore we're going to divide each term in the function by x to the 1. 2x over x minus 1 over x over x plus 1 over x. When we simplify, this gives us 2 minus 1 over x over 1 plus 1 over x. We've rewritten our original function, but it's the same function. It's just in an alternate arrangement. But this arrangement is one in which we will be able to evaluate the limit. We can insert infinity in for the variables here, because remember, these terms are rational functions in which the numerator is a constant. And we know that as the denominator gets very large, the limit of this function is 0. So this term is going to go to 0, and this term is going to go to 0 as we take the limit as x approaches infinity, which leaves 2 over 1, which simplifies to 2. Therefore, the limit of this function as x approaches infinity is 2. When we look at the graph, we will see that our analysis verifies what we see here. The horizontal asymptote is 2, and as x gets very large or very small, you can see the function is approaching 2. This algebraic technique that we used here is going to be very handy when we're trying to take a limit of a rational function that leads to an indeterminate form. We'll be using it again very soon, so don't forget it. A comparison of 3 rational functions. We're going to find the limit of these 3 rational functions, and the results will lead to a generalization that we've seen before. Starting with this first function, you can see that if we attempt to directly substitute infinity in for the variables, it's going to lead to an indeterminate form, infinity over infinity. Thus, we're going to use the algebraic technique that we saw before. Look at the largest degree variable from the denominator of the function. That is x squared. Let's rewrite our rational function dividing each term by x squared. So this is going to be 2x over x squared plus 5 over x squared over 3x squared over x squared plus 1 over x squared. Simplifying gives me 2 over x plus 5 over x squared over 3 plus 1 over x squared. Now let's attempt to take the limit since we've rewritten this function. We can see that plugging infinity into this term, this one, And this one leads to 0 in all three cases, since they are constants over variables raised to a power. So this becomes 0 over 3, which is 0. Therefore, the limit of this function as x approaches infinity is 0. Let's look at the next rational function. Once again, attempting to directly substitute infinity in for the variables leads to an indeterminate form. Looking at the denominator, we see that the highest degree variable that we have there is an x squared. Therefore, we'll divide every term in our rational function by x squared. That's going to become 2x squared over x squared plus 5 over x squared over 3x squared over x squared plus 1 over x squared. Simplifying gives me 2 plus 5 over x squared over 3 plus 1 over x squared. Again, we now attempt to take the limit in this using this alternate form of our original function. We see that these two terms now go to 0, which leaves us a simplified fraction, 2/3. Therefore, the limit of this function as x approaches infinity is 2/3. And now for our final rational function. Once again, attempting to plug infinity in for the variables leads to an indeterminate form. No surprise here. We look at the denominator and see that the highest degree variable that we have is x squared. Therefore, we're going to divide every term in the rational function by x squared. That means we'll have 2x cubed over x squared plus 5 over x squared over 3x squared over x squared plus 1 over x squared. Simplifying gives us 2x plus 5 over x squared over 3 plus 1 over x squared. Now these two terms do go to 0, but we do have a problem here in the numerator as we take this limit, I should say. We're still going to have to plug infinity in for x. This leads to infinity over 3, which is infinity. Therefore, the limit of this rational function as x approaches infinity is infinity, meaning the behavior is unbounded as x gets very large. The results from our previous example lead to these guidelines for finding limits at positive or negative infinity of rational functions in general. If the degree of the numerator is less than the degree of the denominator, then the limit of the rational function is 0. If the degree of the numerator is equal to the degree of the denominator, then the limit of the rational function is the ratio of the leading coefficients. And if the degree of the numerator is greater than the degree of the denominator, then the limit of the rational function does not exist. Now that we have these guidelines, we don't necessarily have to use the algebraic technique to rewrite the rational function. We simply look at the degree of the numerator and the degree of the denominator and then use the guidelines to determine what the limit is. Starting with this first example, the limit as x approaches positive infinity of x squared plus 3 over 2x squared minus 1. The degree of the numerator is 2, and the degree of the denominator is also 2. Since the degree of the numerator is equal to the degree of the denominator, then the limit of our rational function will be the ratio of the leading coefficients. The leading coefficient of the numerator is 1, and the leading coefficient of the denominator is 2. The ratio of those two coefficients is 1/2. Therefore, the limit as x approaches infinity of this function is 1/2. Now let's look at our second example. The limit as x approaches negative infinity of 5x squared over x plus 3. The degree of the numerator, 2. The degree of the denominator, 1. Since the degree of the numerator is greater than the degree of the denominator, then the limit of the rational function does not exist. That means as this function approaches negative infinity, it exhibits unbounded behavior. We can say does not exist for this limit. Let's discuss this unbounded behavior in more detail. A definition of infinite limits at infinity. If f of x approaches positive infinity, as x approaches positive or negative infinity, then the limit of the function is said to be positive infinity. Now remember, infinity is not a number, so when we say that the limit is infinity, it's really describing the fact that the function is unbounded there. A more accurate way to describe this behavior is to say that the function increases without bound. If f of x approaches negative infinity, as x approaches positive or negative infinity, then the limit of the function is said to be negative infinity. Again, not really a number, but saying that a limit is negative infinity lets us know that the function is decreasing without bound. Therefore, a more accurate way to describe this behavior is to say that the function decreases without bound. In this example, we're going to find the limit as x approaches positive infinity of this function and the limit as x approaches negative infinity of this function. Now, using the guidelines that we saw before, we can see that since the degree of the numerator is greater than the degree of the denominator, then we have a limit that does not exist. It's exhibiting unbounded behavior. But what type of unbounded behavior is it exhibiting? Is it increasing without bound or decreasing without bound? Well, let's use an algebraic technique to help us discover which it is. We'll use long division to rewrite this function. X plus 1 into 2x squared minus 4x. You look at the first term, x, and ask yourself, what would I need to multiply x by to get 2x squared? Of course, that's 2x. That gets multiplied by the entire binomial divisor, which gives us 2x squared plus 2x. Draw the line, change the sign so that you're subtracting this line. These cancel, and you end up with negative 6x. Now let's start the iteration again. What would we need to multiply x by to get negative 6x? Of course, this is negative 6. Negative 6 gets multiplied by this entire binomial divisor, giving us negative 6x minus 6. Draw the line, change the signs, and when you add here, you get 6 as your remainder. So this becomes 2x minus 6 plus 6 over x plus 1. Now let's take the limit as x approaches infinity of 2x minus 6 plus 6 over x plus 1. Notice that essentially, since this term is going to go to 0, we're really looking at the limit as of 2x minus 6 as x approaches infinity. And when you insert infinity in here, positive infinity, you get positive infinity minus 6, which is positive infinity. So this is indicating that as x approaches positive infinity, the function is increasing without bound. But look what happens with this same function as x is approaching negative infinity. Again, 2x minus 6 plus 6 over x plus 1. Of course, we know this term goes to 0 because it's a constant over a variable denominator. And again, inserting negative infinity in for x, we get negative infinity minus 6, which is a much larger negative infinity, giving us negative infinity as our limit. That means as x is approaching negative infinity, our function is decreasing without bound. Let's take a look at this graph. You can see that as x is approaching positive infinity, the function is increasing without bound, and as x is approaching negative infinity, the function is decreasing without bound. So this is a way to determine what kind of unbounded behavior you would see in a rational function. That's it for today's lecture. In light of today's lecture topic, this quote by Edward Kasner and James Newman seemed apropos. The infinite in mathematics is always unruly unless it is properly treated. I am certain that none of us has any intention of treating infinity improperly. God bless you, boys and girls.